Okay. Okay. I think I got it. I think I got it working. Of course, now my event's totally gone. So, okay. Uno momento, por favor. Technical difficulties. This is the first.
This is the most amazing.
No, it's not. Well, it is, but so I should be live streaming right now. Is anybody out there? Okay, here it is. Okay, I found the link. So I'm just gonna post it to HTM forum because I put it in the wrong place. Okay. All right. I had to update the link. Sorry. Technical difficulties. This will get smoother as we go along. Let me repost everything. All right. Assuming you guys can see me and hear me now, I hope. We're going to be talking about spatial pooling. I'm going to turn the music down a bit. Still up for me. All right. I'm going to put this on starting soon just so I can give people a few minutes to get in here. Hello, Falco. I had some difficulties with the other link. I wanted to be able to create these live events beforehand, so I can plan ahead my streams, but it certainly didn't work the way I did it. So, and I don't even know why yet. So I'll have to experiment a bit, I think, and try and figure it out. So, in whatever case. We're going to be talking about spatial pooling. I will open up live stream chat. So I'm connected to live stream chat in Discord. If you would like to join there, let me try and put the link in chat. Okay, in case there is anyone who wants to join Discord. There's voice channels there. There's one called General and there's one called Live Stream. So you can use that. And I think I'm safe to show my screen at this point. Here is our oops, no, that's Spotify. There's Discord. So I'm still working out the kinks of the YouTube live streaming. But thanks for joining. We're going to be talking about spatial pooling at a very high level. But I mean, we're going to get detailed too. But I have these illustrations and these diagrams that I've been working on for a long time. Here are some illustrations. If you followed the Building HTM series, Building HTM System series, you'll recognize these, I believe. And also the diagrams, which are these interactive diagrams that we've been building in the Building HTM Systems series. So we got all the way down to active duty cycles, and we enabled learning, all that good stuff. Turn learning on and see how it affects the active duty cycles. Anyway, there's much more that I could do to these diagrams, these parameters, but what I really feel like I need to do, I'm going to turn the music off entirely because I need to think and I need to write and I need a little bit more silent space in the brain. So I'm pretty happy with these diagrams. For sure, there's some styling issues that we could work on, but so what I'm going to do is write some things. So at a high level, the things that I want to communicate, or here's the questions that I want to answer are about specifically the spatial pooling operation or algorithm, whatever you want to call it. Hello, David. Thanks for joining. We're not going to do any coding today. We're just going to talk about spatial pooling, and we're going to try and write some of the pros, create an outline of what's going to be put on this page here, on this page, because I want to fill this in and make it coherent, not just a bunch of diagrams. And if we come up with any more diagrams that we might want to build, we'll put placeholders in there for them. If the noise from the window gets too loud, let me know and I will close it. We're gonna write some HTML poetry. That's a good way to put it, Falco. So welcome, you guys. So the questions that I want to answer are, with relation to spatial pooling, what is it? Why is it happening in the brain? And we're going to link this all back to the neuroscience as efficiently as we can. I think it's important, from our standpoint, to always point back to the neuroscience so we can understand, because that's our mission, is to understand what's going on in the brain. So if you're interested in understanding this, we got to link it back to the brain. Why is it happening? What's the point? Where is it happening? And how does it work? So I think these are good questions. I think we can answer all these questions, and that's one of the reasons. I have a window cam. If you want to see out my window, there's some noise. If we hear a fire engine, we're going to go there. I'm easily distracted, so that's where if I hear something, I'll go to the cam. And I am going to basically be writing this in markup. So write the things here. And we're going to be watching it sort of fill out here. So I don't need to necessarily answer all these questions in order. What is spatial pooling? Why is it happening? Where is it happening? And how does it work? I'm not going to block it out and say, here's the answer to one question. I just want to make sure that we answer all these questions in a clear way. And so I drew it out first. So let me show you what I drew out first. Drew this on the iPad. So this is sort of answering several questions, like where is it happening and why is it happening? So from a cortical standpoint, you'd say that a layer of a cortical column, because spatial pooling happens within a layer of a cortical column. So we're within two structures here, within a cortical column and in a layer in a cortical column. If you don't know what I mean, you can find the cortical circuitry HTML school video, which I will link. I think I can add a card for it. I'm not going to worry about that right now. That's a detail that we won't deal with. So in the layer that we're talking about in the neocortex, in the cortical column, it will be receiving proximal feed-forward input. Yes, and I struggle to decide whether and when we want to introduce the terms proximal, feed-forward input. These sort of things we need to define as we introduce them. So as we run into those terms, I may simply put a footnote about them to just define them at a later date or something. And then we have to introduce the idea of the mini column, because this is all new, this tutorial. We haven't talked about mini columns. All we've talked about is encoding. So these are all new terms. Mini columns, a new term. The idea of a competition of mini columns to try and represent the semantics of input data. That's a new idea that has to be explained. That's sort of what this whole page is going to end up trying to explain. So we talked about feed forward again. This is proximal. The idea of an input space. I like to use this term a lot. It's not necessarily used throughout the rest of the HTML literature, but I use the term input space to sort of define the potential input to a unit of neurons that we're modeling, right? The proximal feed-forward input is coming from this space of neurons that exists somewhere else, and it's very generic just to say input space. We're going to talk about within the, and these are wrong. These diagrams are wrong. So I'm not going to get into them at the moment. And specifically, these here are not oriented the right way. They should sort of be flipped. But I don't know exactly how to draw them. So so I'm not going to focus on taking these pictures and embedding them in the page. I just want to use this as a guide to describe this. So I'd love to tell a story, right? That's the best way to, let me close this window over here. Telling a story is the best way to communicate something, for sure. I want a little, I need some air. But. So, to tell the story, we sort of have to set the stage, present the actors, and so we're going to have some definitions and some things we need to define. So we haven't even talked about the brain at this point in our setup for building HTML systems. We've only talked about encoding.
Brain.
Hello, Yep. Thank you for the subscription. I appreciate that. So let's go home real quick, 'cause I don't think. Okay, so here's for encoders. We were talking about just encoders. I don't think we talk much about brains in here at all. And in the encoding numbers and categories time, we're not talking about brains necessarily or neurons. We're just talking about representations. Hey, my bot worked. Well, one of them. So I haven't figured out how to get the bot to, hello? So, I'm getting distracted. The bot doesn't work. So something works, but not CloudBot. I have it set up to thank you for subscribing. So thanks, Yep. And the brain thing, you like that? Okay, so again, I'm just sort of reviewing what we have so far in here for the encoders. I like this prose. I like this text. It needs to be reviewed and updated, but I'm happy with the direction it's going. I still have some technical problems with some of these diagrams. This is way broken. And we started on. No, I didn't even get finished on categories or time. So there's still lots more stuff to backfill, but right now we're just going to talk about spatial pooling and describing what spatial pooling is. And I'm just beating around the bush because I need to get started somehow, and I'm not sure how. Maybe the best way is to start with this picture. And let's say I almost have to introduce a cortical column and a layer within a cortical column before I can talk about spatial pooling. But maybe I can talk about spatial pooling without introducing those concepts at all. If I just say a population of neurons, if I just talk about a population of neurons, two types, excitatory neurons and inhibitory neurons. Because that's, if we want to boil it down to the very simplest thing, we can talk about, and this is in a layer of a cortical column. There's pyramidal neurons, which are excitatory, and inhibitory neurons. And that's really how this mini column thing emerges. So let's try and do something like that. So I'm just going to be writing and talking to myself. This may not be interesting, but I'm going to do it anyway because just because we're trying to be transparent and be interactive with you guys. So if anybody has a question, or they want to talk about something related, or they don't know, or maybe they have a suggestion about how this content can be presented, I'm open to that. Keep in mind that all of these diagrams are represented in here. I haven't written them all yet, so I can imagine, for example, that we'll have this diagram, which is going to be a live sort of streaming representation of the data that you see at the top of this page. That's changing right here. This, and this. I'm going to eventually have a diagram that shows that. I haven't put it together yet. And then we'll go on to the combined encoding. So I think maybe we can put a placeholder in for this diagram if we need it. Oh gosh. Okay, hold on. This is my wife. Give me just a moment. Okay, sorry. Small interruption. I forget that I have FaceTime on this computer and it shows up. Anyway. Okay, where was I? So, the point. Okay, so I do want to get to the point, and in these visualizations, I'm defining all of the structures of neuroscience first. Maybe that is the right thing to do. At least that's the way I tried to do it visually, is I define one layer of a cortical column, and I can maybe just put placeholders for a definition of a cortical column. And then I can, let's start somewhere. We have to start somewhere, so let's start somewhere. We're going to start out with the neocortex. The neocortex is a homogeneous sheet of neurons. All right? I'm going to start very simply. And yeah, well, we'll start with that. Neocortex is a homogeneous sheet of neurons. It is... There are, no, I don't want to use the passive voice. It is separated into individual processing units, referred to, let's just say called, I'm going to keep this simple, called cortical columns. Okay, so at the moment, I'm happy to just link to Wikipedia pages for the time being, and we might end up changing that. But let's for the moment link to Wikipedia pages. Ahref cortical columns. All right. So now we have a link to a cortical column, separated individual processing units called cortical columns. Oh no, I'm not in trouble, Falco. I'm in good standing. Each cortical column processes, let's say computes, no, let's say does essentially the same computations. Performs essentially the same computations. And are separated into many layers of different types of neurons. Let's leave it at that. First paragraph. Done. I could probably keep going. Different layers perform different processes and are, I want to say they're wired up differently, or they receive different, and receive and have different, like their input and output is different. Like that's one of the, some of them may be doing similar things as other layers, but the input and the output makes a difference in what they represent. Different layers perform different processes, and which also depend on their input. Let's just say, let's keep it like this. Different layers perform different processes. They can receive input. Let's say they may be wired to receive input from different locations in the brain, or directly, well, I don't want to say directly, let's just leave it at that. Different locations in the brain, or let's say sensory input. All right, I don't want to get too far into proximal and distal yet. I just want to kind of make this as a quick introduction. You know, we want to sort of give a context to spatial pooling. Where might, you know, at what level is it occurring, let's say. Okay, so we've talked about layers. Okay, let's also give a link to neocortical layers. Cortical layers. I'm not sure. Let's say neocortex layers. Neocortex layers. Cerebral cortex. I don't know where exactly to link to, but I want to at least give some context. Cerebral cortex. Layers of neocortex. Okay, so let's link here to Wikipedia, the layers part. So let's put that here. Separated into many layers of different types of neurons. Let's do A. Layers. Different types of neurons, and we'll link that whole thing. Layers of different types of neurons. So that will pop over to layers in the neocortex, which works for me. Okay. Now, different layers perform different processes. They may be wired to receive input from different locations in the brain, or they can't, let's say they can be, I don't know, can be wired to receive input from different locations in the brain or sensory input. I'm not crazy about that verbiage, but I'll edit it later. Right now, I just need to get some structure out. So we're sort of answering the questions, where is it happening, and what is it, sort of at the same time. These are my questions that I'm trying to explain. Okay. And then back to this. Let's see. Do I want to say proximal yet? I don't think I want to say, let's not say proximal until we absolutely have to. Let's just say feed forward input. So let's introduce the term spatial pooling now and say that it's occurring within at least one of these layers. Let's start a new paragraph here. Spatial pooling is a process that occurs in at least one of these cortical layers throughout the neocortex in every cortical column. Okay? Maybe explain the difference between excitatory and inhibitory neurons. I will have to, but let's get to mini columns, which is which is coming up really soon. So we're going to have to we'll have to define that. So that's sort of the next thing is mini column competition. So let's say a layer performing, I'm going to capitalize spatial pooling because it's so important. A layer performing spatial pooling receives feed forward input to its to a, let's say, population of pyramidal neurons. Now we've introduced the term pyramidal neurons, and we have to say something about pyramidal neurons, or at least link to more information about pyramidal neurons. I hesitate to link to, I mean, let's define them a bit more. Pyramidal, let's say, feed for input to a population of, maybe we should just say neurons and then define pyramidal in a moment when we talk about excitatory versus inhibitory. So layer performing spatial pooling receives feed forward input to a population of neurons. This feed forward input drives neuron activations, something like that. This feed forward input causes, let's say that. This feed forward input, let's give it a context, may be sensory input or input from other cortical columns. From other cortical areas, let's say that. Because I don't want to say too much, because I mean, it could be from more than one cortical column, really. So let's just say it could be sensory input or input from other cortical areas. Okay, other cortical areas. This, and I want to say I want to say that when we say feed forward input, what typically that means is the input drives neuron activations. Feed forward. That's what I think that's a good point, Falco, because I think we have to say something about feed forward input is typically considered driver input, and the way in that it drives cell activations. It's what directly causes cell activations. This input, it drives or causes neurons in the layer to activate. Now we have to say excitatory. Maybe not yet. Let's not yet. Let's just leave it generic, and we're going to talk, in the next paragraph we'll introduce the idea of excitatory versus inhibitory neurons after we say mini columns. Let's talk about mini columns first, and let's talk this. Okay. Spatial pooling is a process that occurs in at least one of these cortical layers, one of these is, throughout the neocortex in every cortical column. A layer performing spatial pooling receives feed forward input to a population of neurons. Do I want to hyphenate this or not? I need to just be consistent. Let's emphasize this though, because it's an important concept. And I wonder if this works. No, it doesn't. I could do this. Cut, paste. All right. Maybe say that many inputs to one neuron drive the output. Many inputs to one neuron drive the output. I'll when we talk about potential pools / receptive fields, we'll get to that for sure. But I'm trying to stay as far away from it, from the details as possible, and define the hazy stuff, or define some high-level things, and then we'll have some context to talk about the low-level things. So we will definitely get to that. Let's see. This input drives or causes neurons in the layer to activate. So, and I could contrast this feed forward versus, a distal input. Proximal is typically feed forward, we call feed forward. There's also feedback, which we're not going to talk about at all. So maybe we should just call this proximal. No, I don't know. I'm going to leave it like this for now. For spatial pooling, you honestly, you don't have to understand proximal versus distal at all. So let's leave it out. So if we don't need it to understand the concept, let's leave it out. Okay, so we'll just talk about feed forward input. Okay, so this causes neurons in the layer to activate. Okay, let's take a look at the picture again. So we've got one layer of a cortical column, feed forward input. The next thing we have to introduce is mini columns. In order to do that, we have to talk about how these neurons are grouped together. So each neuron, so we could talk about, and now we're getting right into that detail, Falco. We could talk about how a neuron cannot connect to all possible input. See, I have to define the idea of a potential pool pretty quickly. So do I talk about, because we could talk about a potential pool for one neuron first, or we could talk about the mini columns first. So let's talk about the input first, because that's maybe, I don't know. I mean, in my drawings, I've got the input way down farther. Column competition. Talk about dendrites and segments. Well, I'm just thinking, like for spatial pooling, there's only really one segment. For temporal memory, we've got to think about lots of segments, and the idea of coincidence detectors. But for spatial pooling, we're essentially thinking about one proximal segment, and because I'm not going to get into local inhibition at all in this yet. So I think we want to think about this really simply. Let me think here. Maybe it's time to talk about mini columns. So spatial pooling is a process. The input drives or causes neurons and layers to activate. Before these neurons are activated, we could say, like, I'm trying to think about how to introduce the idea of a mini column. We can say, yeah, I think so, Falco. And I haven't, if you look at the spatial pooler, it's just talking about, it's grouping all proximal input sort of on the same segment. Pretty much. I mean, that's what the overlap is. It's not breaking out a whole bunch. It could. I mean, we could break out a bunch of different segments, but we're doing a bit of a more simplified thing than the brain's actually doing, which is what we do, what everybody does. So I'm not going to introduce segments at this point because I don't think you have to understand segments for spatial pooling yet. This drives or causes neurons in the layer to activate. Okay. Go to another paragraph, and we're going to try. Okay, let's try and introduce mini columns. This doesn't have to be perfect. We can add when you write, get it out, and then you can do editing passes. So it doesn't have to be perfect. In a cortical layer performing spatial pooling, there are structures. Sorry about the passive voice, but that's just how we talk. So I like to write how we talk. There are structures called mini columns, and I don't know how to do a cortical mini column, and so they're using this all one word, so I'm going to use it all one word too. Structures called mini columns. Columns, href. These structures, let's just say let's group together neurons and enforce and enforce, let's just say force them to pay attention to the same subset of the input. All right, that's not great, but it's a start. So in this paragraph, we've defined feed forward input. We haven't said input space. Haven't defined a term. Haven't used the term input space yet. Just input. The goal. I wouldn't say the goal is to produce a sparse distributed representation. That's what it does, but I wouldn't call it the goal. The goal is really to create a computational space where it has control of the representation and it retains the semantics of the input. Now the fact that it creates an SDR, is sort of a byproduct of that. That's because that's an efficient way to do that. What spatial pooling is doing is sort of constructing a place for another computation to occur. So it's a computation that makes way for more computation. And the important thing is that it retains the semantics of the input. It retains information. It's very lossy, but it retains the semantics of the information without knowing anything about it. That's another important thing. Without knowing anything about it, about where it comes from or what it represents at all. Okay, so for a mini column, these structures group together neurons and force them to pay attention to the same subset of the input. Back to the drawing here. Okay, so maybe we should say something about the input space. Let's say something about the input space. It's hard to talk about this without creating some terms, you know. So I'm gonna say input space. The input space. Let's call it feed forward. Let's call it feed forward input space. Feed forward input space for a layer of cortex performing spatial pooling. So the feed, so I'm introducing feed forward. The input space is the complete set of neurons that it may be connected to. It may be connected to. And I know this, I'm ending in a preposition. I'm not worried so much about the grammar. Falco says, I like to think of it as stabilizing complex inputs to something relatively constant or maybe consistent. Yeah, it does. That's a good way to think of it. Feed forward input space for a layer of cortex performing spatial pooling is the complete set of neurons it may be connected to. This input space contains, let's just say, could be direct, and so I'm going to use that with a caveat. I mean, it's not exactly direct, it's coming through the thalamus. But let's say it could be direct sensory input containing a massive amount of potential connections. Okay. The spatial pooling process. No, do that. This, no. Let's keep it on mini columns. Mini column structures prevent. Let's say restrict. Did I say they group together neurons and force them to pay attention to the same subset? All right, they restrict neurons. I don't want to say that. Say there's sensory a massive amount of, instead of potential connections, we could just say information. The input space could be, let's just say the input space contains a massive amount of information. Mini columns, the group, what they're doing, mini columns enforce its group force. Mini columns force mini columns for anthropomorphize. Can't talk. The groups mini columns create Okay, I'm going to write this and it's not going to sound good, but it's going to get my thought across. Many columns force neurons within their groups, force their neurons, their grouped neurons. Like I said, this is not going to be great, but to only pay attention to, and I shouldn't use the word attention, to only receive a subset of the information, input information in the input space. These groups will each mini column has a different subset of information of let's say each mini column receives a unique subset of the input from the input space. Does that make sense? This input space contains a massive amount of information. Many columns force their grouped neurons to only receive a subset of information in input space. I'm going to wordsmith this later, but this is what I'm trying to get across. So I am going to use the term potential pool. We'll refer to the subset of a mini column. We'll refer to the subset of a mini columns. We'll refer to the input as a mini columns potential pool. We'll refer to this subset of the input as a mini columns potential pool. Okay, you don't think we need what this sentence? This input space contains the mass. I think that's important. Many columns force their group neurons to only receive a subset of information in the input space. Each mini column receives a unique subset of the input from the input space. Okay, like I said, we'll wordsmith this later, but at least I'm introducing a term and I've pretty much defined it. So we introduced several things in this paragraph. We introduced mini column, feed forward, input space. Oh, we introduced feed forward here, input space here. The input space is an invented term. It's not like a common neuroscience term. Okay. Many columns force their group neurons to only receive a subset of information. Input space, each mini column receives a unique subset of the input. I don't think I need to say from the input space. There. Unique subset of the input. We'll refer to this subset of the input as a mini columns potential pool. Okay. Okay. There may be, let's say there may be thousands. Many columns force can be dropped. Many columns force their group neurons to only receive a subset of information. Oh yeah, you're right. Each mini column receives, oh boy. It's fire truck time. Oh, it's a police officer. I'm sitting with the other way. Okay, you're right, that was a redundant sentence. This input space contains massive amount of information. Each mini column receives a unique subset of the input. And I could talk about, oh, there is a fire truck out there. There it goes. Hey, you're in the wrong lane. Watch out. If I were going to talk about inhibitory neurons, this is where I would introduce them, probably. I'm going to make a note here. But I think I can get away without doing it. I think I can do it. Let's try and knock it. That's okay. I don't mind the typos, Falco. I would definitely be going through this over and over. So if you see a typo, it's okay. I'll find it eventually. Okay. Introduce inhibitory neurons, perhaps. So let's say there are thousands of let's say there may be, I don't know. There may be thousands of mini column structures within a layer of a cortical column. Spatial pooling operates let's say spatial pooling can be defined as a competition. I love calling it a competition for many columns to represent the input space, represent the information in the input space. Let's say that. Spatial pooling, let's just say, is a competition where many columns between many columns to represent the information in the input space. I like that. As neuronal activations in the input space change over time, different many columns represent different input at each time step. Okay. So this is sort of still, we're talking about where and what. Well, yeah. Where and what. Now, maybe thousands of mini column structures within a layer. Maybe I'm gonna close my window just a moment. I don't want to talk about time, Falco, too much because spatial pooling doesn't involve time. Where time becomes crucial is in temporal memory. Time isn't a big deal in spatial pooling. It's crucial for HTM, but it's crucial for the temporal memory part of HTM. So I don't want to emphasize it here. Maybe that's a good point. So let's just say change. We could just say change. Different mini columns represent different input. Different mini columns will different input. And let's not even say time step. So that's a good point. As the neuronal activations in the input space change, different mini columns represent different input. So I do want to say something about this being a lossy process, or the fact that information is lost. I think that makes sense. This process loses information. Hi, Mark Brown. I'm just like brainstorming, drafting out. Here's where we're at. Let's do a quick review. This is just a draft, so really I just want to get a script out of my head, make sure I'm answering the right questions, and have something I can edit, basically. So the neocortex is I'm introducing a lot of terms here, which is tricky. The neocortex is a homogeneous sheet of neurons. It's separated into individual processing units called cortical columns. Each cortical column performs essentially the same computations and is separated. Now I'm seeing typos that I want to fix. And is separated into many layers of different types of neurons. Different layers perform different processes. They can be wired to receive input from different locations in the brain or sensory input. This isn't the end of This is just a draft, so I'm not happy with this, but I need to get something out. Most of writing is editing, so if I can just get something out, it would be a place to start. Spatial pooling is a process that occurs in at least one of these cortical layers throughout the neocortex in every cortical column. A layer performing spatial pooling receives feed-forward input to a population of neurons. This feed-forward input may be sensory input or input from other cortical areas. This input drives or causes neurons in the layer to activate. The cortical layer performing spatial pooling in cortical layers performing spatial pooling, there are structures called mini-columns. These structures group together neurons and force them to pay attention to the same subset of the input. The feed-forward input space for a layer of cortex performing spatial pooling is the complete set of neurons that it may be connected to. This input space contains a massive amount of information. Each mini-column receives a unique subset of the input. We'll refer to the subset of the input as a mini-column's potential pool. This could be a place where we introduce inhibitory neurons, but I don't know if I'm going to do that yet. Because we can wave that off and just ignore it and just say that these mini-columns exist and not explain why. I mean, I don't know how deep someone wants to go. They don't have to understand the neuroscience to understand spatial pooling. I really just want them to understand the process of spatial pooling and sort of how it originated in the cortex. And I don't even want to get too specific about the layers that we think that it's occurring in. I just want to define the process for the most part, like so people can understand why it might be happening. They don't really need to know what layers it's in to answer these questions. I don't really need to tell them what layers it's in, right? So I'm going to try and keep it as simple as possible. I'll try and keep it as simple as possible. Well, this will certainly. So you don't have to understand inhibitory neurons to create this mini-column competition. So at the core, this document is going to be describing how to create a spatial pooler, the logic of the spatial pooling operation. And to understand the logic of the spatial pooling operation, I don't really need to talk about inhibition at all. The inhibition part is the neuroscience component. It's the why. How it does it, we don't have to model inhibition. We just model the effects of inhibition. So I want to sort of leave the door open so that people who want to understand the neuroscience can get there because they understand the terms, at least to Google. But I don't want to go too far into the neuroscience because I want this to be like a functional guide. So this is sort of setting up why this matters. Like, why do we care what spatial pooling is? And we're like, here's what it looks. Here's why the brain's doing it, and sort of how it's doing it, where it's doing it, and what it's doing. So. Inhibitory neurons, I think I should say something about them, but I'm going to skip that part for right now. And I am reading your comments. I might not comment back on every single one, but I'm taking them in. Okay, so where I'm at here is still trying to define what mini-columns are and why they exist. So the main point of all this is the first pass, put in too much and then edit the excess off into link boxes. Yeah, I could do that. That's a good point. So I could talk about. We could have a whole section about excitatory versus inhibitory neurons right here. That would really be the natural next thing to describe. So what would we say here? Like neurons modeled by the spatial pooling operation can be either excitatory or inhibitory. Let's try that. Neurons, I was spelled modeled wrong, by spatial pooling, simulated? Maybe simulated is the right word. Yeah, okay. Neurons simulated by spatial poolings can be either excitatory or inhibitory. Excitatory neurons activate and represent semantic information. Inhibitory neurons act as, well, let's say inhibitory neurons enforce any column groupings for the SP pooling process. I could say that. Something like that. Yeah, I want to talk about the K-winner, but I'm far from that at this. Going through my notes, I'm far from the K-winner. I want to introduce the mini-column competition, but not talk about K-winners because I've got a diagram all about that in a little bit. So, so I do want to introduce this idea of a competition in the next paragraph. And this can at least be a statement about excitatory versus inhibitory neurons. Excitatory neurons activate and represent to represent semantic information. Inhibitory neurons enforce many-column groupings for the spatial pooling process. This is like watching the sausage getting made. Maybe thousands of mini-column structures within a layer of cortical. I think I'm going to leave that paragraph for that right now. Spatial pooling is a competition between mini-columns to represent the information in the input space. As neuronal activations in the input space change, different mini-columns represent different input. Okay. I have to say, like, the next thing that we're going to talk about is potential pool of, and I'm going to have some drawings for this, but I would really like to be able to describe as clearly as possible without the drawings. Some information gets lost with the benefit of stabilizing the information, but that mini pools make up for that loss. I don't know, that's a little misleading. I wouldn't say it makes up for the loss. I mean, you always lose information. You don't make up for it. Like, there's information that you constantly miss, and nothing's making up for it. You just miss it. But I mean, I get your point. And the idea that there's many pools is an important thing, and that they're all overlapping and they're all seeing many, let's say the point being many columns see the same information and react to it in different ways, right? But what am I getting at here? I need to get to the point of defining a potential pool because we have a diagram about that. So here's our potential pool diagram. So I want to get to that point. I think what I want to do is, at this point, introduce this data. I know what I'd really like it if I had this diagram created, but I don't. But I can assume it's there at least. I can assume this is there, and then because I mean, before I get too far into this stuff, I want to have a tangible example of some input to the system changing over time. So this would be a great time, I think, to introduce a data stream. Permanence? No, not yet. Permanence we'll talk about. I mean, I've got a diagram all about permanence, so we'll get to that when we get down there. I think I should talk about, define sort of a data stream, and then talk about, I mean, I want to get down to the level of defining a mini columns, potential pools in code. I mean, let's, for example, I mean, we're going to go, I want to actually look into simple HTML, go into the spatial pooler, and there is a function called create potential pools and create permanences. So, I mean, I want to be able to point, like, put some code in and say, here's exactly how one might create a mini columns potential pools. So I want this to be extremely tangible for people with explicit examples, just like we did in encoding numbers. Just like this, you know, this is the exact function I used to create these encoders. I want to do the same thing here. So what I would like to do, and I think I'm going to do this, I think I'm going to put a placeholder here. So bear with me. I'm going to copy this picture, because this is essentially what I want. I guess you can see what I'm doing. Okay, so I'm going to copy this. I'm going to share it with myself. There it came. There it is. Okay. And I'm actually just going to like inject it right in here. Where can I save this? Let's make it smaller. Like 800. Save. Move to. No, come on. Really? NTA. I know it. This is silly. Okay. Static. I don't even have an images folder yet, so let's make an images folder. And we're going to move it there. And now we're going to look and see it here. And I'm going to change the name of it. Streaming diagram temp.jpg. Okay. Okay. So I think I can see that if I go to duplicate this and go to images, streaming diagram temp JPEG, I hope. I might have to restart the server. Or it might be in static slash, I don't know. It might be in static. Let me, I think I have to restart the server if I. Oh, where did I do that? Class, coding numbers. Okay, is it in static? images. Now I have to go figure out how I set this up. So code syntax does this. Fonts, font. Okay. Just a moment. I'm gonna have to figure out where the fonts are being hosted. Network. Oh. Here we go. It is static. Static slash. Static slash. Yeah, it should be in static slash images slash streaming diagram temp. Static slash images. Oh, there it is. It just took a while, I guess. Okay. So kill this, kill this, kill this. And we'll go back to the spatial pooling page. And I am going to put this there for now. I think this will work. Yeah. Okay. Because this is what I want to refer to. I want to pretend this is here. All these words won't be here. I probably should clean that up. Ugh. Let's just take this. Let's just take this thing. That's what we really want. Okay. Okay. So assuming that this is here and moving with the input. Okay. I'm actually going to have this before it. So now I have to introduce this somehow. And this is going to be essentially a scalar value moving over time. And I can refer back. I think we should be able to assume that that the encoders are understood, because this is past encoders. So let's say, and I don't mind putting headings in here. Let's just call it spatial pooling. This is really H1, shouldn't it be? I mean, it's the top of the. Let's make it the real thing, the real deal. Spatial pooling. Mini columns. Let's put another. We're introducing mini columns here, so let's call this mini columns. I'm a big fan of headers and subheaders. Okay. Simulated input. Let's for now let's create another header called simulated input data. And that's what we'll talk about for a bit. Or let's just say simulated input space, because that's what really we're going to talk about, how this data is represented in the input space. Let's do that. Oh, weird. Okay. So that's good. Go away. Delete. So a hypothetical. So let's do sort of a let's imagine sort of scenario. So we need a tangible example to try and describe this whole process. So that's what we want to set up now. So let's imagine a single scalar value. Let's imagine a single scalar value changing over time. I know I'm talking about time here, but I mean, we do have to put spatial pooling in a context, and it does learn over time. So, and we're going to be expressing that at least. So I think we do have to say something about time. Random spatial poolers are useful, but they're better if they learn over time. Let's imagine a single scalar value changing over time. Based on previous examples of encodings. Well, that's not a great way to say it, but I'm going to do it anyway. We can split this value up into, we might split this value up into 5 semantic, we might, let's say, whoa, not caps. We might encode this value in different semantic ways. For example, the scalar value could be encoded separately from the time semantics as visualized below. Okay. And I will better label these, and we'll assume that this is, I'd like to make this sort of a part of this diagram, so we'll work on that later. Okay. Okay. And so then to display a tangible example, let's, oh no. Example, these semantics can be combined into one encoding that spans the entire input space for a group of neurons performing spatial pooling, a population of neurons performing spatial pooling. Do you want to discuss the importance of change and movement? No, not yet. Not in this at all, because that's like a whole other dimension of things. This is really not going to incorporate any sensory motor stuff, and the concentration of the features as this motion is detected. No, I think that opens up a bigger can of worms. I want to do this without motion, first of all, because I mean, that's still like sort of researchy. Sorry, I just ate a piece of candy. It's Spatial. It's reversed, but I still got this. This is the same one. Okay, semantics can be combined into one encoding that spans the entire input space for a population of neurons performing spatial pooling. And here we have an example of a combined encoding. I sort of wish I had a bigger input space, but I can change that later. I'll change that later. All right, let's describe this a little more. Okay, so after we introduce the combined encoding diagram, which isn't really interactive except for just we can make it gray or combined. So the point of this was to emphasize that the spatial pooling layer does not know how the encoding is performed, what semantics exist in the encoding. So that's what I want to emphasize here. So I'm going to actually use this. This is like one of the things I love about React. The one major thing I love about React is that I can just throw this into my text anywhere. And what I want to say here is that even though many different semantics of this input data stream is encoded in the input space, the spatial pooling layer has no knowledge of that encoding. Let's just say, as you can see by toggling many different semantics of information are being encoded into the input space. Okay. However, the spatial pooling operation has no knowledge of these semantics or where the information comes from. Let's just say, or where the information comes from, or where the input comes from. I know I'm ending on a preposition, but I don't care. So now I can pop this. Let's just put this in a parentheses so it's a little bit more explicit. I'm going to change this eventually. Now I can just remove this. I'm going to change this little toggle. I'm not crazy about the toggle. This is something. What did I do? How did I break? Oh, it didn't really break. Okay. So we can toggle it. And I'm going to, like I said, I'm going to change the UI user experience of that at some point. But as you can see by toggling it, many different semantics of information, however, they are encoded into the input space. However, the spatial pooling operation has no knowledge of these semantics or where the input comes from. It must extract the semantics. Spatial pooling uses overlapping, and here we go, potential pools of different mini columns to extract the semantics of the input without, I love to use this term, prior knowledge. Without prior knowledge of its structure. How's that? Machine learning, guys. Without prior knowledge. I'm going to emphasize that because that's super important. That's super important. Without prior knowledge of its structure. All right. Okay, so now we have to talk about potential pools. And fortunately, we have this great display here that shows, and writing this prose is going to help me better describe like better create the diagram. So I know these diagrams aren't in their end state. We're going to find ways we want to improve them as we surround them with this prose. So we've just introduced the idea of potential pools. So let's further describe that. And here we are. I'm not using, I can put combined encoding under the under the header simulated input space. Let's not say simulated, let's just say input space. Combined encoding, and now potential pools, I'm going to make a higher level header. We'll make it an H2 up, same as input space, because it's an important concept. So we introduce potential pools, and now we're going to talk about it. All right, each mini column, I know this is repetitive, has a unique potential pool of connections to the input space. Its neurons will only ever connect, I don't know if that's a good English or not, will only ever connect to input cells that fall within this potential pool. Now, the way that this has been described to me, I don't need these headphones anymore. The way this has been described to me is, I mean, like, if you have a layer of cells, and I mean, there's a ton of information there, and there's no way that neurons within a mini column could ever connect to all of those. Some of them are just too far away, they're growing in different directions, so you don't want to allow, when you're creating this computational structure, you know, when you're writing the code for it, you don't want to allow it to connect to everything. Thank you. Okay, only ever connect to input cells that fall within this potential pool. This is observed. I don't know what else to say about this. It's observed. Say it's observed in the brain. It's just logically they will not be able to connect to everything. So we only allow it to connect to a percentage of the input. Something like that. Now, one thing I'm missing here is, yeah, where did I thought I had a value for connection. I thought there was an input so that I could change in here in the potential pools. Don't I have diagram with mini column count? Wow. Mini column count. Okay, let's fix that real quick. Mini column count. It didn't even am I even passing that in? No, I'm not. I'm not even using it. That's how. Okay, whatever. This was the first diagram I made, so how did I, so I've got props dot in diagram width, encoding diagram with potential pools, selected mini column. Oh, that's right. I think I changed this. So that's right. That was before I had the computation happening. Oh gosh. So connected percent was what I was looking for. That's something I need to parameterize because I don't think it's using this anymore because Right, that's not even happening anymore. We're doing that outside of this diagram at this point. I didn't think, so that's going to be something, I swear I had a connected percent. Connected percent. Yeah, there it is. So it's a state. It's a state. Okay, so what I don't have is a toggle or something to change this, and I want a way to change this. So I need to do, basically I need to create one of these number value thingies for it. So let's steal this, and we'll call this connected percent. Connected percent low. That's fine. That's fine. Let's make it 5% connected percent. This should be pretty easy actually. On update, we changed to connected percent. So now we're going to essentially just add this. We can add it anywhere we want. Okay, so we'll say in this case, let's say in the diagrams below, the percent of connected, it's not actually percent, it's like the rate, I'll just, whatever, of percent of input many columns could connect to is connected percent. And that's something that they should now be able to change. All right, so I can move this, and then you can see it change. So that's what I want. That's exactly the type of interaction that is important, I think, in these diagrams. So now I'm going to say I'm going to point them in the diagram below. Click on different mini columns on the left to display different, there are different potential pools of connections on the right. As input passes through the input space, you can see how each mini column is restricted, seeing only a portion of the input information, something like that. Okay, so I like this. I like being able to do this. That changes everything too. That changes the whole deal. which I like. We should probably have like a reset button. It's because somebody's going to come through here and just mess with everything. We can do that later. So we're going to keep it at 85. Okay. So I definitely want to add legend to this. And that's in my list of things to do, so. And nothing breaks. Yeah, I hope not. It'll break if I go to 0. I bet it might break. No, it doesn't break. These break because that's not right. I mean, it's right. I mean, it's just sort of those are the winner mini columns. They're all 0 overlap. You got to pick something. So what if I put 1? Fully connected. Still works. All right. Okay. Okay. Okay, we're making progress, which is good. So now I actually want to show the code. So let's, we might as well show some code here. I can probably take this pretty much verbatim and show a little bit of code to show the potential pools. So let's say, because this is supposed to be a tutorial on how to do this, how to create it. Setting up mini column potential pools is not complicated. All right, just leave it at that. Done. No, let's go look at component showcase, because that's where, oh no, I have an example of this in encoding numbers, I think. In encoding numbers, there is, so first of all, I need code syntax. And then there's examples in encoding numbers. Examples, coding numbers. All right, I forgot about this. So I've got to create a new file and call this spatial pooling.js. And what this is going to do is we're going to take the explicit, we're going to embed basically our code examples in these literal strings and then export them. So we're going to do this. Okay, so in spatial pooling, okay, code example 1. Oh, yeah. We only have code example 1 right now, so we'll just leave it at that. Encodings, we won't have encodings, so we're just going to have code example 1. And I'm just going to say const code example 1 equals this and that. Okay. And we'll change this as we go along, as we need to, but I think this should work. Okay, so now close this. Can close this for now. In the coding numbers, I want to grab code syntax and the examples. Put this all the way up at the top. Layout, data stream, inputs. Some code syntax up top. Well, let's put it after the layout. And code examples. This is going to be from spatial pooling. Okay, so now we should have examples dot something. So in this case, what did I do? Examples dot code. That's basically it. This is all I want. Something like this. And I'll actually probably turn these into figures and figure captions, maybe. No, that's not really a figure. It doesn't, worry about it later. But let's put it where we want it to be. Let's go away. Okay, so we want a code example here. Code example 1, examples code 1, code example 1, code example 1. Okay. Let's see what breaks. What breaks? It didn't break. Okay, setting up mini column potential pools is not complicated. And then we have a nice code example. At least, I don't know if I'm going to scrutinize this a whole lot right now. First of all, I can already tell things I don't like about it. So let me fix some things. What happened to... Well, let's... let pool equal. Why is there two? That's weird. This is too many indentation. Oh, it's just tabs are super huge. I don't want tabs to be that huge. It's okay. I'm not gonna worry about that right now. But let's say we set up the pools. This shouldn't really be ops.size. This should be mini column count or something like that. So let's just do that. Yeah, let's call it mini column count. And we'll call this input count. And then just connected percent. So that sort of generifies it, so it's not connected to a specific code implementation, and it still makes sense. So we go through all the mini columns, we create a pool for each mini column, we go through all the input. If we're below the connected percent, we're going to push input index. Okay, so let's be real explicit with this. We're not even using this I at all. So like, we'll leave it. But this we are using, so we could say input index at least and be explicit about what we're pushing. So we're going to push the input index into the pool. Right. All right, that basically sets up potential pools. All right, I'm gonna add one more descriptive thing to this as we're talking about it. Right before we show the diagram, we'll talk about the green check marks. Notice the green check marks and white X's. In the input space. These indicate input that is observed by the selected mini column, or let's say observed and ignored by the selected mini column respectively. All right. As you let's even go even further than that and say, as you decrease the connected percent, you should notice that more input is ignored by each mini column. I don't know if that's relevant or not, but it's true. So it's something. Okay, so now we have we've just described potential pools. We have shown the code example that is almost exactly the code used to create the potential pools. And now what? Let me see here. Let's go back to this combined encoding. Okay, like I said, these legends don't exist yet, but I'm planning. I will create them, so those will be a part of the page, but they need to be part of the diagram. On click. I'm not doing this on click. I'm showing the input all the time. I think it makes sense to just always show it. Okay, so now we have to talk about, and I'm a little bit, I don't like this terminology that much because it seems like I'm the only person who uses it. So maybe it's not right. So I don't know if I want to, I'm not going to use the term receptive fields. I think potential pools is fine, but I want to talk about the permanences within the potential pools. That's the important thing. So that's what this is about, permanences. One thing I didn't do here, one thing that would be nice for this diagram would be to not show the connections initially. That would be a good idea. And then have a button to toggle the connections on and off. That would be a good idea. So I'm going to make a quick issue for that so I don't forget it. Okay, so along with labels for potential pools, let's create another one, and we'll call it do not display connections on permanences diagram initially. I'm gonna change this into an issue right away. Convert to an issue. There should be an option for reader to turn on off connections from outside the diagram. Diagram. Okay, so that one, I'm fine doing that. That's going to be an enhancement, and it'll be a React thing. I don't have React anyway. Okay, so it's just an enhancement. Works for me. Did we explain why we get the clustering? I'm clear on the method, but the why of it. Let's see. Hold on a sec. Why we get the clustering of what? What clustering do you mean? Maybe I'm confused. The clustering of the connections, because that is pretty much random. I haven't really described any of the permanent stuff yet. Because I don't see any clustering happening in potential pools. That's also just random. Of course, the input has clustering. So here, what I want to describe is within the potential pool. Let me put this back up to 8.5. What does it mean to make a pool? The pooling part. Oh, that's sort of further down. I mean, that's going to be when we talk about the competition, right? That's where the pooling really starts. We're not doing any pooling until we do the k-winners operation. That's the pooling, right? Does that make sense? So I mean, that's certainly like the crux of the biscuit that we want people to understand. What does it mean to make a pool? And it's the k-winners that is the pool. That's what's making the pool, right? It's really basic, but if you're new, it may be a source of confusion. Yeah, certainly. But wouldn't you agree we're not pooling yet. We're only pooling even when we create permanences. Hello, FD God. Sorry, I almost missed you there. How's it going? Thanks for joining. We're not pooling until we do the k-winners, right? This is just establishing initial connections. Even the connection distribution is not pooling. It's just, there's nothing going on here except initialization. When we actually run the competition, that's when the pooling starts. Okay. All right, let's do a quick review here. I'd like to keep going, so I think I will. So quick review of spatial pooling. We talk about introduce mini columns. So here's the terms we're introducing: cortical columns, layers within cortical columns, sensory input, I guess is sort of a term. Excuse me. We keep talking about spatial pooling, but we never really introduce what it is we're doing. Yeah. Let's see. It's hard. It's certainly, yeah, it's definitely a chicken and egg problem, right? How do you describe what pooling does without understanding pooling? It's about the semantics. So that's the way I like to describe it. Maybe right up front, you're talking about at a high level, trying to describe why pooling, why. That is a good point. We could certainly right up front. Let's investigate that. We could have an introductory paragraph that describes why are we pooling, like the why right up front, right? So I would say spatial pooling is a mechanism to extract semantic information from dense input into, let me just start writing. Spatial pooling is a process that extracts semantic information from an input array of data. We can wordsmith this later. Wordsmith it later. You'd put something right under the big bold title. Yeah, there we go. I'm right with you. Why does it do it? Okay, so it does it so it has to provide, and maybe this is a little bit dense, but I'm going to write it anyway. In order to provide a a controlled space to perform further temporal operations. Process that extracts semantic information from an input array, let's just say from input to provide a controlled space to perform further operations. Additionally, like I said, I'll wordsmith this later, but let me try and get, the essential features out. Additionally, the representation is converted into a sparse, let's say, additionally, input is converted into a sparse representation, which carries further benefits. And I should probably put like C previous, C something, citation needed. Which provides further benefits. Provides further operation, further computational benefits. Spatial pooling is a process extracts semantic information from input to provide a controlled space to perform further operations. Additionally, input is converted into a sparse representation, which provides further. I said further twice. Maybe says sparse data representation, since SDR is such a recognizable term. Sparse, maybe says sparse representation. Wait, I don't get it. I'm saying it. Maybe I should put distributed. Is converted into a sparse distributed representation. I think we should say SDR here. Additionally, input is converted into a sparse distributed representation, which provides further computational benefits. But the main thing, even though, so maybe this is where we should also mention that even though information is lost during this transformation, extract semantic, pooling, by, what is it, what should I call this? This, because there's such redundant coverage, because there's so much overlapping receptivity, many, even though information is lost during this transformation, I want to say something like, information is lost, but important semantics are still retained because of the redundant overlapping receptive fields. Because of, but I'm introducing terms there I don't want to introduce yet. Drop redundant information. Drop. This is lost during this transition. Did I write highly redundant information? I don't understand what you're saying. You want me to drop highly redundant information? Or you mean write that, even though this information is lost during a transition? Oh, you're saying that it ignores redundant information and extracts semantics and drops redundant information, something like that. Just, even though this, even though information is lost during this transformation, you're offering wording. Okay, the information is lost during this transformation. Highly, it's a highly redundant information is. Ugh. The redundancy I'm trying to say is that all the mini columns can potentially represent the same information. Many columns can potentially extract the same information. Is it still really that laggy? I thought I changed. I thought it was last time I checked it wasn't as bad. I've got it on ultra low latency. But I guess I can't do anything better. I don't know what to say. I don't know quite what to say here. Even though information is lost during this transformation, the SP, the SP, I'm going to put spatial pooling mechanism. Stability is gained and semantics is preserved through redundancy. That's not bad. I'm gonna steal that. Stability and we'll wordsmith it later. Stability is gained and semantics are preserved through redundant well, let's say redundancy. I mean, we sort of explained that redundant. It's one of those words you say too much. It sounds funny. Redundant. So that's any word. Through redundancy. Okay. Spatial poolers work to allow the strongest mini columns to respond and drop highly redundant information. I don't want to use the term mini column yet. Is the only thing. I want to describe it without saying any of the keywords that someone would have to look up. And that because I start doing that in the next paragraph. So I'm going to leave this for now. We'll come back. We'll come back and do wordsmithing. But I like the idea of having an introductory paragraph that anybody can read that describes the key purpose, why is spatial pooling happening, without having to look up any terms. That's too generic, Falco. It's just too generic. Okay, let's see, where are we at? Mini columns, input space, combined encoding, potential pools. I love that you can put stuff in the text. This is what I really am going for. Okay, so permanences. We have to talk about permanences now. Okay, each cell, let's say each connection, each potential connection. Well, first I should probably describe this a little bit better. Instead of just saying it's not complicated. Setting up a mini column potential pools. Setting up mini column potential pools. It's not complicated. For each mini column, input is, let's just say each mini column. Let's say upon initialization, each mini column is has a percentage, has a chance. Each mini column each mini column's potential pool of connections is established using a simple random random number generator. Downtown. It's using a simple random number generator. Oh. I was just joking with you, Falco. I knew that you weren't serious. Thanks, you guys, for your help. It helps to have somebody just to knock ideas around with. Setting up mini column potential pools is not complicated. Upon initialization, each mini column's potential pool of connections is established using a simple random number generator. For each cell in the input space, a mini column either has a possibility of connecting or not. Again, wordsmith later. I want to just define what this is doing. The code below defines a mini column's potential pool as an array of indices towards an array of indices of the input space to which it might connect. Okay. Does that make sense? The memory of neural networks is stored in the connections between cells. That's a good thing to throw up right at the beginning of this permanences section, because that's something that's good to remember. Let's put that first thing. I like that line. The memory of all neural networks. That's yeah. is stored in the connections between cells. I like that. Just throw that out there. Whoops. Code example 1. This should be here. Right? Code example 1. Yeah. Oh, no, that was actually should be here. Code example 1. Establishing mini column potential pools. So maybe I should put that up before. I kind of like that before. Yeah. Okay, the code below defines a mini column potential pool as an array of indices. Okay. Okay, back to permanences. The memory of all neural networks is stored in the connections between neurons, or cells, whatever. So these within the potential pool. Let's say within each mini column's potential pool, we must establish an initial state for each potential connection. For each, we call, okay, again, wordsmithing later, right? You know, the cells versus neurons, cells, maybe I can put something up front and say when I talk about cells, I'm talking about neurons, but you know, neurons are cells. Wordsmith later. We must establish initial state for each potential connection. We call each potential connection a permanence. If a permanence is, I don't know if I want to say that yet. I'd like to introduce the idea of a connection, perhaps down here. If a permanence reaches a connection threshold, we say that the connection is established. And the neuron is connected to the input cell. Okay, for now, I'm gonna leave it like that. Okay. Within each many columns potential pool, we must establish an initial state for each potential connection. That's sort of, so we call it each potential connection a permanence. So now I have to describe a connection threshold, which I haven't introduced yet. I'm wondering, I'm sort of introducing, it's the hard thing is so many concepts at once, you know. Does permanence have a counterpart in biology? Yeah, it's the strength of a synapse. It's the strength of a synapse. So you can always say that the state between two cells, if they could possibly connect to each other, there's a synapse potentially growing there. There's a dendrite growing. So the permanence is how close is that synapse from being established or not, right? Strength of synapse that might never connect. No, it could connect. So we're representing the synapses that will never connect with the potential pools. So this number defines how many of them could potentially connect or not. That's what the potential pool is. That establishes a pool of potential connections, of potential synapses. Strength of a synapse. Strength of a synapse. That's a good way to say it. let's say that. Memory will essential state a permanence. This represents the strength of a synapse. Okay, so we've just introduced the term synapse. Okay. Yeah, that's true. So yeah, that's part of the exercise, isn't it? Just working through it and trying to figure out what words need to be on the page and which ones don't. This represents the strength of synapse. So I'm trying to work towards introducing this next diagram where we can, so initially, I think I'm going to break this up into two diagrams. I think I might break this up into two diagrams because I don't, or maybe not, I don't know. So I have to describe how we decide what the permanence values are, because that's the goal of this, is describing how you create a spatial pooler, how you create the logic of a spatial pooler. So the next thing you have to do is decide what are the permanence values within that potential pool. What are the permanence values within the potential pool? So we have to establish these initial connections. Yes, so I'll talk about them changing over time when we get to learning. That's going to be in a later section. That's going to be in the next section, actually. Actually, we really should talk about learning after we talk about the mini-column competition, because you have to apply learning in the context of the competition. So probably we'll talk about the competition and then talk about learning. Must establish initial state for each potential connection. We call each potential connection a permanence. This represents the strength of a synapse. Okay, let me just write down what I'm thinking. If the permanence is, did I already put this? Memory vulnerability established is above a defined, and this is connection threshold. We can put this right in there. Above a defined connection threshold. Connection threshold. And in this case, we can even give them a way to change it. You flew over it quite fast and I didn't understand where it came from. You could state that these permanence values need to be stored to and can change in time. Well, that's what we're doing. So we're going to have a code example right next, right coming up soon, that establishes these connections and creates a data structure. So we'll get there. Under the definition, give a very broad introduction of what it is you're going to describe in the detail below. If you use more than 2 sentences, you're overdoing it. You mean as far as permanences? So that should include this sentence. That's a good point. So these, okay, hold on. I think I know what you're getting at here. So speaking of permanences, memory is stored in the connections. This represents the connections between cells. This is where we could say synapse, or we could at least define. Storing the connections between cells, called synapses. How's that? Okay, it's called synapses. Say in our model, let's just say we model synapses as scalar permanence values, if they breach a connection threshold, we say they are connection threshold, they are connected. And then we talk about the initial state. Okay, so now I don't have to have this now. Call each potential connection a permanence because of permanence values. Scalar permanence values. Let's see. Permanence values, and I can take this out. We call each potential connection permanence. Okay. Okay. The memory of all neural networks is stored in the connections between cells called synapses. We model synapses as scalar permanence values. If they breach a connection threshold, they are connected. Within each mini-column's potential pool, we must establish an initial state for each connection. I don't think I have to say potential connection. I've said potential enough. I think it's contextually there. This represents the strength of a synapse. If the permanence is above a defined connection threshold X, I've already said that. It's a common techie thing to say one really greatly detailed sentence, too dense for anyone to really take in. It's not a sin to say it easy as a warm-up exercise. Yeah. And then the body slam, right? That's a better approach, isn't it? Boil it down as simply as possible, and then add more detail. That is exactly what I'm trying to do. That's what I'm trying to do. That's the best technical writing is hard, and most of it is bad. Most technical writing is really bad. So we're trying to boil it down here. Okay, so I want to throw this in. I want the users to see this connection threshold. But maybe I should introduce this after they see the diagram. Okay, so let's show them the diagram. This represents the strength of a synapse. So I want to show the diagram without permanences first, or without connections. Let's do this real quick. I think I can do this really easily. Show connections. False. Okay, so now if I go into... Oh, I got an even better idea. Show connections, show... oh, no, we'll just do the whole thing. Whoops. Yeah, that's right. Okay. Show connections. So if I have show connections false, I'm not going to show those connections. I'm not going to show the connection distribution either. Okay, so let's try this. This should be easy. So in the permanences, okay, so where's my render function or update function? Okay, here we go. Update, render mini columns, render input space. So in the input space, render connections. I programmed this pretty well because I can do this easily. I'm a little proud of myself. Okay, this dot ops, we're gonna say if this dot ops dot show connections. Then we'll whoops. Right, and we'll do this. It broke. I broke everything. Okay. It's not ops, it's props. Props. Okay. Cool. Okay, so there's no connections. Okay, so one more thing. If show connections, draw histogram. So if show connections, draw histogram. Same thing. Go away. Okay, cool. That's what I want. But this is also going to change my width. Okay, so diagram height equals diagram width if show connections, diagram height equals diagram, well, let's do this. Make it very explicit. Cut it in half. Oh, it didn't work. Oh, if not show connections. If not show connections, I have to, oh, of course. There we go. Okay, beautiful. Okay, so now we can see the permanences. The only thing I don't like about this is I think I might be doing the highlighting wrong. Oh no, I'm not, because it's a Gaussian. Excuse me. Yeah, it's a Gaussian distribution. So okay. Does this make sense? Cow sound. I forgot about the cow sound. I have the cow sound. Even on YouTube, I have the cow sound. All right. You'd leave in potential. I don't know. I've said potential so many times. Like I said, we'll wordsmith later. Okay, so strength of the synapse. So I need to describe in the diagram below. In the diagram below, connection permanences are displayed in a heat map where green is closer to 0 and red, let's say green is less connected, and red is more connected. All right. And then I need to show I would, and I'm not going to do this right now, but I would like to show, be able to toggle the connection on and off. But that's going to take a little bit more coding. So I'm not going to do it right now. I will, however, create our next one. This is called permanences, and this is called permanences and connections. And this is going to have show connections true. And this is permanences and connections, and we'll call this figure 3.2, and this one figure 3.1 for now. Close enough. Just make sure that these, okay, so everything's still synced up and everything. One shows connections and one doesn't. So this is permanence values, and this is permanence values connections and initial distribution and initial permanence distributions, let's say. Okay. Permanence, yeah, it's a weird word, I guess. But well, not really. I mean, if you think about it's a range. How permanent is the synapse? That's what you think of it like that. Like how permanent is it? You never think about permanence as a spectrum, do you? It's either is or it isn't, right? But in this case, it is a spectrum. Okay, this is looking pretty good. I'm pretty happy with this progress. I've been going for 2.5 hours now. I'm gonna keep going a little bit longer. but not too much longer. We're going to get to the mini column competition, and I'll cut it off there. And then we'll have editing and stuff to do. So, okay, quick review. Under permanences, memory of all neural networks is stored in connections between cells called synapses. We model synapses as scalar permanence values. If they breach a connection threshold, they are connected. So here's what I want to add down here. Now I can put the connection threshold. If it breaches a connection threshold, we say that the connection is established. Ooh, connection threshold is not defined. Oh, it's a capital C. You know what? I hate doing this. I don't hate doing it, but I think we need I want to have show distribution. I'm going to have show connections and show distribution as separate things. First one's going to be false, false. This one's going to be true, false. And then the last one, we're going to have 3 of these. Yeah, okay, so I am going to do this. So instead of this show connections, this is going to be show distribution. Whoops. Distribution. And then on the histogram, that's fine. Show distribution. So now we should have one with connections and one without, no distribution. And then I'm going to update the permanence values and connections, but not the initial permanence distributions. Okay, and then we're going to have a third one. Do you think this is overkill? I don't mind it. I don't mind the overkill, honestly. Permanences and connections. Permanences, connections, distributions, and distributions. Yes, it's happening. Permanences, connections, and distributions. Permanences, connections, and distributions. Figure 3.3. Permanence values, connections, and permanence distributions. Now we'll have 3, right? No, I have to put true. Okay. All right. A little redundant, but, and maybe we'll come and clean that up later, but another thing I want is to be able to hover over this. Again, I'm going to go add this. Another thing. On permanence diagram, on hover over input, show permanence value. I'll just leave that there. Because I want to be able to hover over this and see like 0.5, 0.8, point whatever. Okay. Okay, within each mini-column's potential pool, mu must establish an initial state for each connection. This represents the strength of a synapse. In the diagram below, connection permanences are displayed in a heat map, where green is less connected and red is more connected. If a permanence breaches a connection threshold, 0.5 whatever, we say that the connection is established and the neuron is connected to the input cell. In the case below, connections are initially established in a normal distribution around a center point which ensures that learning occurs quickly. Stay tuned. I don't know. I'm not going to talk about that yet, but I will soon, which ensures learning occurs quickly. See later section on learning. Okay, I'll just leave that. I'll leave it at that for now. In fact, okay, so we've got a connection threshold. We also have a center point, which is distribution center, which I can add here, which will establish around a center point, which ensures learning occurs quickly. Yeah, I'll describe it later. If I'm using tooltip style, yeah, tooltip style pop-up. If you're using the word heat map, shouldn't less be blue as in cold? Maybe. I've seen heat maps done in green and red pretty commonly. I think it displays better because if you do blue and red, there's a purple in between, and it doesn't. It's not as nice because you got red, orange, and so it kind of cools down. And purple, you know, I don't know. I typically see green and red. Okay, so if I change the center point, that changes the distribution, which we haven't described yet. The threshold we have described. So now we need to put these both at 0.5. Now we need to show the distribution. The distribution, okay, so I got an even better idea. Okay, this could be pretty easy now that I think about it. In the last one, let's just show distributions. Just permanence distribution. That's what we should show, just permanence distribution. So there won't be any, so show connections, false. Show distributions, true. Show, oh, you know what? We'll just say if we show the distribution, that's all we're going to show. So I don't even need this. I don't need show connections. So I'm going to change that. And the third one that we do is only going to show the histogram. That's even better. That's exactly what I want. Okay, so permanence. So we're going to say, let's take this, mini columns, input space. We're only going to do this if we're not showing the distribution. We're going to show that. Else, we are showing the distribution. We're only going to show the histogram. Perfect. Okay, so either case, the diagram height is going to be this. And then I can get rid of this entirely. And I can make this a constant again. Oh, yeah. Okay, so that changes how the distribution is shown. That's okay, I can fix this. So I just need to not transform. Beautiful, okay, perfect. That's exactly what I want. All right, so we've split up this diagram into 3 parts, which is great. This is great. They're all linked. It's very modular. And as we change anything, they all change. Okay, this is great. I love this. And we're able to inject the pros in between. Okay, so now we're talking about the center point. We should really take some of this out. In the case below, in the case above, connections are to establish a normal distribution around a center point. In the diagrams shown above, I'm just going to delete this, and I'm going to add this paragraph here. So that we can change the distribution as you change, you can see, okay, so I want to show the relationship between the connection threshold and the center point of the distribution. So initially, you want the connection threshold to be the center of the distribution. So we'll say something like that. For the initial the connection threshold should be near the, what did I call it? Distribution center. The distribution center. Oh, I've already got it. Should be near the center. I think I just said that. Connection are usually established a normal distribution around center point, which ensures, yeah, learning occurs quickly. I'm going to take that out. For initial permanence, the connection threshold should be near the distribution center. This ensures that synapses are primed to either connect or disconnect quickly when learning. See later. Okay, I'm just gonna put see later, knowing that we're gonna defer something. Okay. Okay, so I'll show you. So you should be able to see this Y. As I turn learning on and the mini column competition starts, if they're disconnected a lot, right, like this, and I turn learning on, it's less likely anything's going to happen because nothing's connected. Let me go down a little bit further. Okay, so now we have something connected at least. Is anything getting connected? Like the winner mini columns are all just sort of random crud. Let's go down further. You see what the problem is? You want them to learn quickly. So the closer I get to it, the more likely the more entropy. You want entropy. That's what we're going for here. So if you center the connection threshold in the middle of the distribution, there's going to be immediate entropy because things are going to start changing right away, and you want that entropy for the system to stabilize, or else it gets stuck. It gets stuck in some state that you don't want it in. Maybe I should say that. Maybe I should say entropy. Either connect or disconnect quickly when learning. Ensuring more entropy in the initial of the system. Something like that. Entropy's not, I don't know, I think entropy might be the word. It's you want things to start moving quickly and randomly, right? If you're up here, things don't move quickly or randomly. They're locked in. And this is like less entropy because there's less things changing, less things happening. So you want it. Where are we? Connection threshold 0.5, not 0.5. This gives us the entropy. No, think of stable is when the same mini columns are active all the time. That's stable. You want the entropy. That's what boosting does. Boosting enforces entropy. It pushes, it prevents the stability of the same columns firing all the time, and it pushes that semantics out to the other columns. It increases the amount of entropy in the system. And this is the same concept, I think, is you want that entropy. And also, I think entropy is a term you hear in machine learning a lot too, and it's the same type of concept. You want your systems to have entropy. Not too much entropy, or obviously, then you can't make sense of anything. But you want a sweet spot. You want a certain level of entropy so that the system has a space to compute in. If it gets locked in to some state and it can't get out, that's a problem, and that's when you need to somehow enforce entropy or introduce entropy. And I think that's what I'm talking about here, I hope. Okay. Okay, I'm going to stop here, and I'm going to commit this. Let's do a quick rundown of it first. I'll do a quick review, and then we'll move on. I don't want to get too caught up in editing. I'm not going to do a quick review because I know I'm just going to get caught up in editing if I do this. Mini columns, input space. This diagram doesn't exist yet, but it will. Combined encoding, combined split. No prior knowledge of the structure, potential pools. So all these affect everything else on the page. I could, at this point, and I probably should show, let me do this real quick, the permanences. So then I have to describe this like Bates distribution, which I don't. We'll do that next time. We'll do this next time. I'm tired. Okay, yeah, we'll do that next time. I'm pretty happy with where we got. We didn't write a ton of prose, but that's good. I don't want to write a ton of prose. I just want to write just enough to link concepts to the diagrams that we're creating. That's the whole point, is setting the conceptual stage for these diagrams, and the diagrams are supposed to like drive the concepts home. Okay. The permanence breaches a connection threshold 0.5. We say each connection is established and the neuron is connected to the input cell. In the diagram shown above, connections are initially established in normal distribution around a center point 0.5, which we can change for the initial permanences. The connection. Wait a minute. Oh, it changed. Okay. Connection threshold 0.5 should be near the distribution center. This ensures that synapses are primed to either connect or disconnect quickly when learning, ensuring more entropy in the initial state of the system. Okay. I'm glad that helps, Falco. That's good indication that we're on the right track here. All right, let's commit this. I'm happy with this. Happy enough to commit these changes, and I'll do it in a pull request just to make it clear the changes that we've made. Let's do a quick code review first, like we're supposed to. Okay, first of all, permanent, I'm gonna make this a little smaller so I can see it. These are the permanence changes that we made. Diagram height, showing distribution, show connections are the options that we added. So we hardly had to make any changes for this, which was really nice. I'm pretty happy about that. So we basically split this up into 3 diagrams really easily. Potential pools, I just removed some cruft I wasn't using. I added in examples for spatial pooler, and then we imported the example, and then most of this was all in spatial pooler. So connected percent number input, and then prose. Added this temporary diagram. Prose, and then splitting this figure up and more prose. So that looks fine. Everything looks good. So let's say first pass at SP pros up to no, what was it? Up to what? Up to mini column competition. Okay. And we will just push this. Got everything. Git push origin SP pros. That's going to get us a link to create a pull request. And we will. And I'm just going to merge it. Create pull request. Here's our changes. I already reviewed those changes. Merge it, confirm it. Now, delete the branch. I should see, I'll go ahead and push this too. Let's get those changes from upstream. There they are. Git push Heroku master. This should deploy it because I'd like to see this deployed to our Heroku app, which is where? Where's it at? There it is. It'll be a minute or so before this actually deploys. Sometimes it fails and I don't know why. And eventually it's just deployed and it just works, so I don't know. Hello, GR, I don't know how to say your name. How's your architecture compared to current state-of-the-art architectures? State-of-the-art what? Papers and links. Yeah, I can give you some links. Go to numenta.com/papers. If you want specifically, oh, why can't, it wouldn't let me put that link in. .com/papers. Oh, that's weird. It wouldn't let me. It's numenta.com/papers, but I'm having a problem sending anything right now, which is weird. Let me see. Go to. Can I send you? I'm new at the YouTube. Oh, I'm not signed in. That's crazy. I got signed out while I was live streaming. Okay, hold on. I'm almost there. I can get back. That's nuts. Okay, I'm back signed in. Let me try this again. I was like on my live stream page. Whatever. Yes, show. That got held for review for some reason. Numenta.com/papers. There it is. And it's not even a real link. Numenta.com/papers. The specific paper that you want is I'll send it. I'll just link it to you. It's from 2015, isn't it? 2015. Why? No, 2016. Why neurons have thousands of synapses. This is the paper that you want to look at. This is what describes these ideas of spatial pooling, etc. And the link to the code base that I'm working on is here. There we go. Is the encoding of the RDSC getting converted to scalar before sent to spatial pooler? The RDSC is, I'm not using that. I'm just using a very, very simple scalar encoder, which you can see how it works here in encoding numbers. I don't have a document for the RDSC yet. All I'm using is a normal scalar encoder. And you can see it in the spatial pooling diagram right here. This is it. This purple bit, the purple block, that's the scalar encoder. It's just going up and down and up and down. So very simple. It's not distributed at all, randomly or otherwise. It's just going up and down. All the rest of these semantics are all about the date. Day of month, hour of day, weekend, day of week. And these colors might not correspond to it because I'm still setting this all up. So what type of data is being sent to the SP? This data right here. this scalar value that's going between like, it's just a sine wave. It's a modified sine wave. It's a sine wave. I've added a little bit of noise to it, and I've synced it up to days, right? So it goes up and it goes regularly up and down with the days. And then like every third day I add like amplify it a little bit, so it's got not only daily patterns but weekly patterns, and we'll start to see those as we move through that I did that on purpose because the temporal memory will recognize those patterns, but I haven't gotten to that yet. We're still just doing spatial pooling. So all it is this is the data, a scalar value going up and down, and then something like Sunday, July 8th, 2018 at 1:48 p.m. That's the data point. And it's just moving through time and space. Time and space being the scalar value moving. That's the spatial information. Any other questions before I hang up? And you guys can go see this right now. I just put the link in, right? This is what we just created. So you can go take a look at it and mess with the settings like I was just doing. It looks like it's all deployed and it's working. You can turn learning on. It gets more interesting. I haven't talked about that yet. And we haven't written the pros for the competition or active duty cycles. How do you see hardware designed spiking neural network units influencing the efficiency of architecture? Greatly. Not so much the spiking. We don't do spiking. I mean, like, we don't model the spiking. We just model on or off, not like how fast it's going on and off. But the hardware is definitely a big deal. Once you have neuromorphic hardware, that'll make a big difference in the performance of these HTM style systems. Is there a formula to convert encoding to scalar value? Yes, absolutely. I mean, just look at this. Go to encoders, and encoding numbers. And there's the code. That's the whole point of this tutorial. And you can see there's interactive stuff here. How to make it bounded. So this one is a bounded scalar encoder. You see how when I get to the edges, it doesn't slide off the edge. It's bounded. The normal one is not bounded, so it slides off the edge a bit. So there's different types of encoders, different ways you can do it. So I've got all this stuff here. You can change how many values you want. Yeah, just play with this page. Go to this page. I just linked it in chat. And we've got this one that's cyclic encoding, and I've turned it into a circle. This is all work in progress. Some of these are broken. So there's the idea of discrete versus continuous encodings, and the difference there. This diagram's broken. But the basic scalar encoding code is right there, and you can see it. If you follow the links in here, it'll go right to the simple HTM implementation. And there are encoders right there. So these are all the encoders that I've worked on for this building HTM systems thing. And there's the cyclic scalar, bounded scalar, etc., and then the time encoders and category encoders. Okay. Let's see. Yeah, what Mark said about spiking is correct. Could you see advantages to the spiking? I see the ability to encode more information. Yeah, you can definitely encode more information. For what we're trying to do, we don't need it yet. We might need it eventually. It might, like, oscillations are certainly important in your brain, and we're probably going to have to eventually model oscillations. But for this level that we're talking about for spatial pooling and temporal memory, we don't see any reason to model it yet. Certainly is important in other aspects. That additional derivative-based temporal domain spiking could be helpful. So you mean is the output an array or a number? It's an array of bits. on or off. That's what the encoding provides. If you look at this blue thing down here, that's like an array of bits. The blues are on and the whites are off. So in this case, 27.4 gives you that specific output, right? Yeah, feel free to extend HTM with spiking. Certainly is possible. There's a lot of different projects. I mean, we call HTM biologically constrained. It's not perfect. It's not biologically perfect. We try and understand as well as we can what's happening, and we're not implementing anything that goes against the logic that we understand is happening in the cortex. But we understand there's more happening than we're modeling. But based on what we're trying to do, we're not modeling the spiking stuff. We could certainly get more functionality out of a system, perhaps by adding spiking or oscillations, for example. And oscillations and spiking, I think, are very integrated. And it's not due. It could be partially due to the limitations in the hardware, because it does that will take more computing power. But that's for the bit encoding. No, the bit encoding, the representations, the binary representations, that's super important. That's not just because of hardware. That's just you get these benefits from using sparse distributed representations that are really important. And let me point you to some papers. Numenta.com/papers. Again, there's a whole section here on sparse distributed representations. So go there and read some stuff. There's sparse distributed representations are super important, and that binary representation that the brain uses is really, really important. It just is. And so read up on it there. I would suggest. And if you want more formulas for encoding data for HTM systems, right here, this is everything that I learned about encoding I learned from this document. So, and here's, if you want some more stuff about SDRs, read these other papers. There's a ton of information about SDRs and why they're important. And if you want to know how they benefit machine learning systems, this is our most recent paper. How can we be so dense, and the benefits of using highly sparse representations in deep learning systems? Okay, log z, is it fed to the SP as is, or fed as an array format? Well, it depends on the implementation, but it's an array of bits, or an array of on or off. That's it. So, yeah, it's just an array of bits. The data format's confusing. The array of bits is confusing. Have you seen the HTM school videos on SDRs? Because that would be helpful. Which is like on this YouTube channel. Just go look at the HTM school playlist and watch the so maybe watch them again. I mean, the binary thing is really important. And they're just bits. They're just bit arrays. I've been interested in sparse representations since a problem I've been working on requires encoding from a graph convolutions network. Interesting. Have you posted to DARPA yet for funding? No, we're not going to do that. Thanks you guys for watching. Don't forget to like the video, subscribe to the channel if you haven't already. It helps me personally, because Jeff and Donna and the other folks at Numenta can see that what I'm doing is helpful to you guys, and I get to keep doing it. So, it's a long time ago. I remember we had some conversations with DARPA, but we're not looking for funding at the moment. Okay, I'm gonna hang it up, everybody. Thanks for joining again. I usually do this on Twitch, but but I'm trying YouTube, so I'm gonna do another live stream on Friday. Actually, we're gonna do Hackers Hangout on Friday, so which will be on YouTube. So everyone, take care. Unless there's any last minute questions or anything, take care. and have a great week. You're sending the feds in. Bring it on, I guess. Goodbye.